Hi friend, today I am going to start part 2 of module 1. In part 1, we have defined partial differential equation. We have also classified those equations. But to describe some natural phenomena, we need to solve a partial differential equation of some physical quantity together with some auxiliary conditions. There are two types of auxiliary conditions. One is called initial condition and the other one is called boundary condition. If the physical quantity is prescribed at some particular time, then those type of conditions are called initial conditions. On the other hand, if that physical quantity is described at some particular point in space, then those type of conditions are known as boundary conditions. In this video, we are going to explain those auxiliary conditions. Now we shall take one example. So this is example of a physical system where the partial differential appears together with some supplementary condition. Consider a thin, homogeneous, perfectly flexible string which is under uniform tension along x axis in its equilibrium position, and the end of the string are fixed at x equals to 0 and x equals to L. Now, the string is pulled aside a short distance and then released. So, the string will now under free vibration. So, the motion of the string can be written by the differential equation del 2u del t square equals to c square del tu del x square, and this equation is known as wave equation. And there are some conditions, those are to be maintained to solve this problem. Those are initial conditions. So, initial conditions, which is the condition which is given at time t equals to 0. So, u x at 0 equals to f x, that means we are assuming the position of the string obeying some function f x, and the velocity of the string is given by the function g x. And we also have the boundary conditions u 0 t equals to 0 and u L t equals to 0, since the two ends of the string are fixed. So, the initial conditions and the boundary conditions are the supplementary conditions. So, we have to solve the partial differential equation together with these two conditions. Now, if the problem is in unbounded medium, then we cannot define any boundary conditions, then the equation is to be solved together with the initial condition. So, that type of problems are called initial value problem or Cauchy problem. So, this is one example of initial value problem. This is heat equation, one dimensional heat equation, and the supplemented condition is given by u x 0 equals to f x. So, this is the initial temperature field. So, according to the supplementary condition, we can divide a problem or a mathematical problem into some categories like initial value problem, boundary value problem, or mixed initial boundary value problem. Before solving a partial differential equation, we have to think about the solvability of the partial differential equation. A mathematical problem is said to be well posed if it satisfies the following three conditions. The first one is the existence, which says that there is at least one solution of the problem, and the second one is the uniqueness, which says that there is at most one solution, and the third important criteria is the continuity, that is the solution depends continuously on the data. So, a mathematical problem is said to be well posed if it satisfies all three conditions. So, it is possible to find a solution of a well posed problem. A problem which is not well posed, that means which does not satisfy any of the above three conditions, is called an ill-posed problem. An ill-posed problem cannot be solved mathematically. Now, I want to illustrate the concept of existence, uniqueness and continuity using some examples. Let us first consider the example ux square plus uy square equals to 1. This is given differential equation, and we have to solve this equation using the auxiliary condition uy is greater than 1. Now, the imposition of too many boundary conditions or auxiliary conditions, or the conditions which do not satisfy the given equation, may lead to the no solution of that problem. So, this is the example. If you see the boundary condition uy is greater than 0, this condition will not satisfy the equation. You will not get any real solution of this problem. So, there does not exist any solution of this problem. Now, to illustrate the idea of uniqueness, we have considered the motion of transverse motion of a string, which is described by the first order wave equation, which is given in the second example, del 2u del t square is equal to c square del 2u del x square, and the string is clamped at the 2 points at x equals to 0 and x equals to L. So, that is described by the boundary condition u 0 t equals to 0, u L t equals to 0, and this is to be solved together with the Cauchy condition u x 0 equals to f x. So, this gives what will be the shape of the string at time t is equal to 0, but these conditions are not sufficient to find the unique solution. That means, what will be the transverse speed of the string, that is not described here. So, for different values of the transverse speed, one can get different answer. So, for this example, uniqueness of the solution is not valid. Now, I am going to discuss the continuity or the stability of the solution. So, for this case, we are considering the same equation, one dimensional wave equation, and the initial conditions is given by u x 0 equals to u cap and u t x 0 is equal to v cap. Let the solution of the first set of equation is u. Now, we deviate. Deviate the initial condition in a small amount. So, we are trying to find the solution of the equation, but the initial condition is slightly different from the original one. So, you can see that u cap is replaced by u1 cap and v cap is replaced by v1 cap, but these u1 cap and v1 cap, these two functions are very near to the function u cap v cap. That means, in mathematical sense, we can define their norm u cap minus u1 cap is less than epsilon and v cap minus v1 cap is less than epsilon, where epsilon is greater than 0. So, and epsilon is some suitably chosen constant, and this is valid for 0 less than equals to x less than equals to L. Now, we can say that this equation is stable, this problem is stable if the solution of the first set of equation and the solution of the second set of equations are differ by very small amount. So, in mathematical sense, we can say that if u1 is the solution of the corresponding changed initial condition and u is the solution of the original problem, then if this condition is hold, that means norm of u minus u1 is less than delta, where delta is greater than 0, some suitable constant, and delta depends on the constant epsilon. So, if this condition is hold, we can say that the continuity condition also hold. So, we have learned that if these three conditions, existence, uniqueness and continuity condition holds, we can say that the problem is well posed, and a well posed problem is solvable. We can find solution of a well posed problem, but the solution of ill posed problem does not exist. So, this is the example of one ill posed problem. This was first observed by French mathematician Hadamard. So, he tried to solve the Laplace equation which is given by uxx plus uyy equals to 0 in the half plane x greater than 0 together with the condition u at 0 y equals to 0 and the derivative of u at x equals to 0 is e to the power minus root n sin ny. This equation has, it can be proved that this equation has a unique solution, and that solution is given by un xy is equal to e to the power minus root n e to the power nx sin ny. So, this solution will satisfy both the equation and the boundary conditions. But it is to be noted that if n is very large, then un xy as well, the derivative of un x tends to 0 for y is equal to 0. But un xy takes a large value when y is not equals to 0. So, there is a discontinuity in the line y is equal to 0. So, when y is equal to 0, the solution is 0, and when y is not equals to 0, solution increases infinitely. So, continuity condition does not holds here. So, this is one example of ill posed problem. Therefore, in this part you have learned about different auxiliary conditions. You also got introduced with the well posed problem. Therefore, in a nutshell, we can say that in module 1 you have got some basic ideas about partial differential equation. In study of PDE, sometimes the knowledge of surfaces and curves are required. So, that part is not discussed in this video. If you wish, you can go through the study material attached with this video. Apart from that, at the end of module 1, you will get some problem for self-assessment. So, in this way, we end module 1 and the first week of this course. See you in the next week. Till then, goodbye.